Masters from IIT Madras, and then pursued his PhD from Louisiana State University. After postdoctoral researches at University of Massachusetts, Boston, and National University of Singapore, he joined IIT Bombay as a faculty member. So his areas of expertise include quantum information theory, current control theory, and quantum thermodynamics. So the duration of talk is 1 hour, including question answer. So I welcome to the speaker by this. So Dr. Vinjanampathy, it is over to you. As I can see the title of your talk, it was visible earlier. Yeah, so I think you can start. It is over to you.
Thank you very much, Utpal. So thank you very much to the organizers for having me. It's again a great pleasure. I'm actually quite a regular visitor to ISA Kolkata. I talk to all of the folks there who do quantum technology, so it's always a nice opportunity for me to kind of find myself with friends. So here today, actually, I'm going to talk to you about seeding boundary time crystals. So this sounds like a strange phrase, and I expect it to be a strange phrase to most of the audience who Utpal just kindly told me a couple of minutes ago are masters and PhD students, right? So I expected this to be the case because this is, after all, it's a summer school. And so what I've done with my talk is I've organized it into a little bit which is pedagogical. So for those who are experts in the audience, I really apologize that I will bore you for perhaps the first 3/4 of the talk. And then after that, perhaps something interesting I can share with you, which is basically the stuff that we've been doing with this. So so the kind of structure of this talk is basically I'll try and share with you some of what I've learned over the last many years about open quantum systems, specifically about open quantum systems in the Lindblad form and how you can solve them, what the exact solutions are and how you go about it, what the structure of the mathematical solutions are. And I'll point out, some friends and colleagues who've contributed enormously, some seniors who've contributed enormously in this field. And then I'll basically talk about generic solutions, and I'll build up to something called the Liouville superoperator. And so that Liouville superoperator will be the story for the second part of the talk. So that's the way that I've organized it. Again, I don't know the structure of the interruptions here, but feel free to interrupt me whenever you want, if the organizer so chooses to kind of move all the discussion towards the end. I'll hope to be done with 10 minutes or so to spare so that we can discuss. Okay, so with that, let me just get right with it. So just as a kind of a demarcation, a visual demarcation for you as well, the transition slides are in gray, the pedagogical slides are in black, and as we go, you will see me transition from black slides to white slides. And the white stuff is the stuff that that is crucial, and then it's the stuff that we've done. So it transitions smoothly over to the stuff that we've done. Okay, so perhaps all of you who are here, masters and PhD students, know the Schrodinger equation. So the time-dependent Schrodinger equation or the time-independent, it doesn't quite matter. And the solution to such a Schrodinger equation is simply just to write, let's say, parameterize the coefficients to be time-dependent objects, plug it back in, and solve for the coefficients. And there are many ways to do this. Now, what happens if I have two or more systems? Well, then you have to write things in a tensor product space, as you've perhaps seen many examples of this in this workshop and also in your coursework. And again, there is a proliferatingly large number of terms here, and now you have to account for all of them. Now, this is what this says. It's just an exponentially large number of terms, and you can digitize the representation to make it look a little bit smoother. Okay. So now the point that I want to make is basically that if there is if the quantum states underneath, which is I have a system and then there are many subsystems around it, so which is what I've labeled as A, B, C. If they are of this form, which is always they're in tensor product form, they're actually easy to simulate. Right? This is a trivial statement for those who know quantum computing. But essentially all that this tensor product structure means is that at any given point in time, you can just think of each system separately. So it's just the linear cost of putting them on n computers or putting them on n separate, small n separate, repeating the algorithm small n number of times. What is difficult to simulate is basically if you start building up entanglement, building up quantum correlations, which of course are, there are many varieties of them, and this is one variety, which is this particular kind of quantum state. So what I've just done here is basically I've tried to sneak in something for bipartite systems, something called the Schmidt coefficient. I need that Schmidt decomposition in hand, but we'll return to this point about simulability later. So now with this context, with this very brief context of, I have a system and then an environment, and then I hope to write quantum states, time-dependent quantum states. When I solve them, they're either basically in this product form or they're entangled to each other. This is all I want you to take away from this conversation thus far. And now I can introduce to you basically the problem at hand. The problem at hand is that I have my atom. Let's say I have a hydrogen atom that I'm trying to study. I have a Rydberg atom. In real experiments, this is very relevant. But this atom is not isolated from the universe. It's actually talking to a bunch of different atoms through any number of different physical mechanisms that we've studied in class. So, Coulomb interaction, dipole-dipole interaction, whatsoever, kind of Heisenberg magnets, so on and so forth. And the crucial point is basically, I don't care about all these white cartoon atoms, basically. I only care about my red atom, because the red atom is the one that I want to do quantum computing with. That's the one that I want to build as a sensor. That's the kind of dilute gas that I've trapped in a chamber that I want to make as a magnetometer. So that's the one that I care about, and I don't care about, let's say, the paraffin wax that's sitting on the walls of the chamber and things of that sort. So depending on which specific analogy you look at, the environmental degrees of freedom are different. So this is what I've summarized here. Not interested in the environmental degrees of freedom. We're only interested in the effect that the environment has on the system, right? And so this effect, basically, how do I capture this? Again, I have to go back to basically what I know, and what I know is Schrodinger's equation. So I know that if the problem was entirely closed, if only the hydrogen atom was given to me, as is in the case of our first year quantum mechanics courses, what I would do is I would just write down Schrodinger equation, and I know how to solve this under various kind of approximations and so on and so forth. Now, what I can do the same for the entire universe, right? So what I've represented in this white box is the system, which is in red, and the environment, which is in white. So the system environment is still an isolated quantum system. There's nowhere for it to, nothing for it to talk to. And so I can write a Schrodinger equation for the system plus environment, and then the argument is basically that you have to try and then figure out the full solution, and then from the full solution figure out what the partial solution is, right? Now this is the kind of brute force way of doing this, but thankfully there is an elegant answer. There is an elegant shortcut to this, and the elegant shortcut is the following observation. The observation is, suppose I'm interested only on the system observables, right? So think about a damped harmonic oscillator. I'm only interested in what the harmonic oscillator is doing. I'm not interested in what's happening to the environment at all. And so the environment, there are rare molecules which are gaining and losing momentum. They're changing position, they're changing directions, and they're colliding with each other and the pendulum. And I'm uninterested in all of them. I'm only interested in the damped harmonic oscillator. Then what I would do is I would look at, let's say, the position of the damped harmonic oscillator, the momentum of the damped harmonic oscillator. So the analog of this in quantum mechanics is I'm looking at a local operator A, which only depends on the system degrees of freedom. On the system degrees of freedom, right? And now I can ask, what is AS tensor identity in the environment? What the expectation value of it is in the quantum state psi SE, right? This is psi I have solved for the full system environment dynamics in my mind. You can't do this in real life, but once I have solved it, let me now just ask what would happen if I only cared about system variables. And as this calculus shows, you can actually see that basically what you have to do is you have to trace over the environment. So the partial trace over the environment as a mathematical procedure, which is the same procedure as the physical procedure of ignoring the environment. This comes from this little calculation. I've just simplified the algebra for myself by assuming some Schmidt decomposition. This is the reason why I introduced it before. So, I can explain it offline if you're interested. And so what you can do is you can write for yourself the expectation value of any system operator in an environmental state. You can write it as basically a convex mixture of basically the expectation value in some pure state. And this is all captured by this density matrix rho s, which is simply a convex mixture of projectors, right? So this is the fundamental structure of how you can think of density matrices as arising from the linear nature of quantum mechanics, along with the fact that there are two or more subsystems. That's it. And if you put those two together, then you just arrive at the need for density matrices. Okay, so you can ask the following question. You can say, okay, now I think of, I can think of a wave function, not of a specific physical system like a hydrogen atom or a helium atom or whatever. I can think of an abstract wave function and I can ask what are its mathematical properties. So in exactly the same way, you can ask the abstract question. I have a density matrix, and I'll drop the superscript s because we're trying to get we're only talking about the system, so we just want to leave that superscript out. So my density matrix rho, what are the properties that it has, right? I know that this structure is something that I wrote just now, but I just give you an n by n matrix. Can you tell me if it's a density matrix or not? How do I do this? And so this was worked out very carefully by several people. And so I just present the answer to you, which is that the density matrix has to be Hermitian, so that its eigenvalues are real. It has to be positive so that those real eigenvalues can be interpreted as probabilities. And finally, it has to be trace preserving, which is basically to say that it has to be trace class, which is to say that it has to be unit trace, right? You have to normalize the density matrix, this operator, which is Hermitian positive, to get a density matrix. Okay, and so you finally basically you can ask the following mathematical question again. You can say, if I give you a density matrix which has the following properties, which is it is Hermitian positive and its trace class, can you tell me how it transforms itself to another density matrix which is Hermitian positive and trace class, right? Then we're discussing one quantum state of a damped harmonic oscillator going to another quantum state of a damped harmonic oscillator. It obeys all of the properties of density matrices. So what is the transformation equation? And this equation has there are many solutions to this, depending on whether you're looking at discrete time, whether you're looking at continuous time, whether certain sets of approximations, factorization approximation, Markov secular approximation, you're allowed to make those approximations. But I present you two important cousins, and essentially the second one is the story for today. So the first one is basically has a very well-known name. It's called the A and B matrices. So this is a very famous paper by Sudarshan, Matthews, and Rao. And I urge you to look at it. It's actually quite an interesting mathematical construction, which actually rings through time even now. I can share with you papers from like 2015 and so on and so forth, which use exactly this construction to do some very nice things. So if you're interested fundamentally in this kind of area, then please talk to me offline and we can talk about this. But this is basically just a density matrix in at one time going to a density matrix at another time, but there is no time attached to it. It's just a discrete transformation. So it's essentially like an input-output theory if you're used to that language. There's a different object which is basically much closer to kind of the classical dynamical systems equations that we write, and much closer to, let's say, Fokker-Planck type equations that we write, which is basically what's called the master equation. So it's a time continuous differential equation for the evolution of the density matrix. So and this with this set of approximations is given by this kind of an equation. So what I want to share with you, if this is new to you, or if you've only seen it in this workshop, is what I want to share with you is that this part is just basically coming from standard quantum mechanics. This is just Schrodinger's equation written for the projector side psi, as opposed to just the state vector psi. So this is, you can work out that this is actually easy to see. Now, what I want to do is not derive this. That's difficult. That's actually a little bit of work. But what I want to do is justify this. So to justify this, what I want to say is what are the properties that this density matrix is supposed to obey? It's supposed to be Hermitian, which means that if I think of rho of t plus dt as rho of t plus d rho by dt, which is this equation, times dt, if I think of it like that, d rho by dt should also be Hermitian, because I'm adding a Hermitian matrix to a Hermitian matrix. And you can check explicitly that this construction is Hermitian. X rho x dagger simply goes to x rho x dagger. And because remember, A, B, C dagger is C dagger, B dagger, A dagger. And this anti-commutator is explicitly self-adjoint. So you can just check that this whole thing is actually Hermitian. Now, the next question is positivity, and this is in fact the trickiest part. It has something to do with the properties of gamma k. Gamma k has to be positive, semi-definite. And this is also trace preserving. You can check that if I go back to my equation, rho of t plus dt is rho of t plus d rho by dt times dt. D rho by dt should be traceless because rho of t plus dt has trace 1 and rho of t has trace 1. So when I move everything can move over the density matrix except its trace. And so the trace should not move at all. And indeed, you can check that this is a traceless construction. Just use cyclicity of trace as the guide for you to get that solution. Okay. So now what I want to do is this is basically part one. So part two is what I want to do is I want to take this and I want to ask what are the exactly solvable models that this differential equation has, mathematically speaking. And what about if I can't solve it exactly, what do I do? And the solution is numerical integration, of course. And what can you say? You have to still set up the numerical integration so that it succeeds. And so I'll talk about that in a second. And so these two things I will consider today. There is also two more things you can do. This is not the only thing you can. You can seek approximate solutions, analytical approximations, and you can also seek to do quantum simulations, right? After all, we are in a quantum computing workshop. And so you can imagine very quickly that, hey, what if I put the whole thing on a quantum computer and somehow that's the, and yes, these are viable options and there are interesting questions and answers to be sought here. This is not outside the scope of a 1 hour talk, so I've left it out, but I point you to two of these papers of mine from the recent past, which actually address some of these from a kind of perhaps interesting point of view. Okay, so with that, I come to my second part of the talk, essentially, which is exact and approximate solution. This is the first part of the complicated stuff that I want to talk about, essentially. I'm sorry. And so what I'm going to tell you about right now is about solutions and solutions exact and approximate to this quantum system. Let me just do a time check. Okay, good. So let's solve the first problem, which is what happens if there are no Lindblad operators. If there are no Lindblad operators, xk is 0, then my Lindblad equation that I just showed you is just Schrodinger equation. This is called the Liouville von Neumann equation. So the Liouville von Neumann equation is just basically if you take a wave function psi and you take a derivative of it, you get h psi acting on the right hand side and then h psi acting from the left hand side, and that just produces this commutator, right? And so if rho, if the initials, if the Lindblad equation is 0, then basically the evolution equation is simply given by this Liouville von Neumann equation, so-called. And now I can ask what's the solution? And the solution is very simple, at least it's very simple to work out what the solution is. If rho naught is basically a pure state, then basically it doesn't evolve at all, right? If it's an eigenstate of the Hamiltonian, sorry, it doesn't evolve at all. If it's not a eigenstate of the Hamiltonian, but it's a pure state, then it's just a typical Schrodinger equation solution, which is expand basically the solution in terms of a basis set, which is the eigenstates of the Hermitian Hamiltonian, and then just plug and play basically within a couple of minutes you arrive at basically the way in which the density matrix changes in time. Now, so all the non-trivial questions that we should ask are the questions related to what happens if there are Lindblad operators. There's non-zero Lindblad, right? That's after all what I started off setting up. Then at least one steady state is guaranteed. So this is something that I want to say to you. So when there are Lindblad operators, what does it mean physically? It physically means that there are dissipators in the system. So it's like a damped harmonic oscillator. There are environmental degrees of freedom which I'm interacting with. And this will always produce a steady state, and there is a guarantee within this framework, there is a guarantee that this will happen. And so before I get to that guarantee, let me show you how some exact solutions are possible. In fact, in Nielsen and Chong, if you look in the appropriate section, you will actually see something to this effect. So what I want to do is I want to solve the equation rho dot is gamma over 2. So I've just gotten rid of the Hamiltonian term just for simplicity, and times x rho x dagger minus anticommutator x dagger x with rho. So I want to take the example where the Lindblad operator x is the poly sigma z matrix. So remember that sigma z square is the identity. So what you get is just a minus rho here because it's the minus anticommutator of the identity operator with rho, which is just rho, divided by 2, which is just rho. And so what you can do is you can write the equation out, gamma over 2 z rho z minus rho. And if you write the density matrix rho as 1 plus r dot sigma divided by 2, and you simply plug it in, then you get a set of differential equations. So you get a differential equation r dot dotted with the Pauli sigma matrices is gamma over 2 times basically some difference of two matrices. This r prime is basically the z rho z dagger, and r is basically just the original block vector, right? So this is assuming that I write the density matrix in the block vector notation 1 plus r dot sigma. And you can very quickly verify that basically r dot of x comma y basically is exponentially decaying. So what it does is it produces r dot of x comma y is minus gamma times r of x comma y, which means that I can immediately write a solution. R of diagonal r x comma y as a function of time is e to the minus gamma t times rxy at time t equals 0. And r dot z you can work out from the equations I've just shown you is equal to 0, which means that rz is whatever the initial value was. So if my density matrix, which is 1 plus r dot sigma divided by 2, if I write it in the matrix notation, it's 1 plus rz, rx minus iry, rx plus iry, and 1 minus rz divided by 2, right? So what I do is to take the steady state, what I do is I basically just I take small t going to infinity, and when I take small t going to infinity, what I notice is that this off diagonal terms will go to 0. This is what you see here, and the diagonal terms simply remain where they are. And this is the first example that you would solve, and it already shows you a fantastic complication. And the complication is that it actually exhibits multiple steady states. So it allows for a family of steady states which basically are parameterized by rz of 0, right? So that's interesting, and that's something to keep in mind. Lindblad operators actually have a more non-trivial multiple steady state structure underneath. Now, let me, with this introduction, show you another solution, which is, let's say my rho dot is x rho x minus x dagger x by 2. This is just the Lindblad equation. I've just taken the Hamiltonian part out, again, because you can always go into a rotating frame with the Hamiltonian and then get rid of it, basically. This is typically the logic of these calculations. So here is an assertion, this comes from Baumgartner and Thirring, that if x acting on some state, which let's call it the ground state, if x acting on 0 is the 0 ket is the number 0, which means that 0 annihilates x, right? So if x is the annihilation operator A, this is the ground state, A acting on 0 is 0. Then rho infinity is just 0, 0, right? So you can immediately see that this is true, because if I write the zero temperature map, the Lindblad equation, which involves 0 temperature, it just has an A rho A dagger there. So x is A, and this is, and if you leave it alone, it just cools down to the ground state and sits there, right? So x infinity is rho. You can just check this by substituting. If you replace 0, 0 in this, then you can just check that rho dot is equal to 0. So this is trivially true, right? So this is what this says. Now, assertion number 2, if no such 0 exists, if there is no vector 0 such that x acting on 0 is equal to the number 0, then there exists a unique steady state as well, and that unique steady state is given by this. And the proof of this is simply by substitution. You can just check that this object, essentially when you substitute back, simply produces the steady state. Okay, so let's apply the Baumgartner-Thirring solution to the phase damping map, right? So our x here was sigma z, which means x dagger x is identity, and so when you basically take the Baumgartner-Thirring solution, what it does is it simply produces the steady state as identity over 2, right? So notice that this analysis is actually missing the mixtures, the various complicated. This simple slide is missing the mixtures, but we've already worked out that the mixtures exist, right? Okay. So here is another solution. Now I'm adding the Hamiltonian term, and I want to show you what happens there, because that's also something interesting for us to see. And especially for quantum optics, one of the focus areas of this workshop, a lot of the times what you have is something like x rho x dagger here. So A rho A dagger here. And then what you have here is A plus A dagger. So you have a harmonic drive, basically A plus A dagger. And you have basically just a dissipation 0 temperature bath, right? A harmonic drive plus a 0 temperature bath is actually a model for many quantum optics systems. And so within this and other contexts, R.R. Puri, who's in IIT Gandhinagar now, who's at IIT Bombay, and Lawande. So Puri and Lawande produced a solution, which I want to share with you now, which is that if you write the CP map rho of phi of rho, rho dot is minus I rho minus I omega times x plus x dagger and minus gamma. So this omega and this gamma is just sitting there so that I can differentiate between the coherent term and the Lindblad term. So what they do is they basically say, let's consider this operator as tilde, and as tilde plus minus is as plus minus minus plus a constant, a complex constant. And with this, what they were able to show is that you can actually absorb this Hamiltonian term into the Lindbladian, right? This is essentially traveling in the reverse direction from calculating Lamb shift terms for Lindblad operators if you're for master equation derivations, for those who are familiar with that technology. What they did was basically they just said that I omega x can be absorbed with this x, and x dagger can be absorbed with this x dagger with some clever rearrangements. That's it. That's all the. And with this, again, we go back to basically the rho infinity solution we have before, and you immediately have a very, very nice solution. And this actually has a tremendous applications to resonance fluorescence theory already. So I'm happy to share some more references on this. There are several that I've already indicated here. And so that's something that I just also wanted to share as an exact solution. Okay, so till now, what I have discussed with you are several examples of kind of exact solutions where you can actually by pen and paper work out what the master equation solution looks like, right? What the steady state looks like, and which is the thing of interest, because what you want to do is you want to ask, if I leave a cup of coffee, what temperature will it reach asymptotically, right? That's the quantum analog of that question is what we're trying to ask here. So the next solution that I want to showcase is basically what I will refer to as the Liouville space solution, and this will be the transition into our work. So here, what you do is you basically say, what happens if you don't have an exactly solvable problem? Even if you do, how do you kind of set up the problem in such a way that you can actually solve the problem in analogy to dynamical systems theory, right? This is what I'm trying to do here. So to do that, let me just make a observation, and the observation is that the Lindblad equation is linear in the density matrix, right? What I mean by that is that rho dot has one row appearing every time on the right. If I take rho and multiply by lambda, this whole equation gets scaled by lambda. There are no lambda squares. So this is linear in lambda, and what that basically means is that I can rearrange the whole thing to just look like a vector equation in the coefficients. So I can take, let's say, a 2 by 2 density matrix is rho 1, 1, rho 1, 2, rho 2, 1, rho 2, 2. And I can rearrange it as a column vector. And then this column vector, I can write the rho dot, within a vector. If I write rho, I mean the Liouville ket. So this object is called a Liouville ket, sorry. And so the corresponding Lindblad equation now becomes basically a matrix equation, right? And so let's do this as an example once or twice, and then we can move on to more complicated, or an exactly solvable problem, and then we can move on to more complicated solutions. So the example that we saw before was basically is 2 by 2 density matrix. I columnize it. Then what you can show, this actually just involves a little bit of algebra, is that any operator that hits the density matrix as B rho C on the, in an evolution equation, should become C star rho B, so that this vector, which is this vector, is acted upon by the same matrix as B rho C, right? So if I take this and act on the left and right by B and C, then I should act on the vectorized version of it by the C star rho B, C star tensor B, right? This is just the kind of maths that you can work out. And you can verify that, for a simple for a simple Schrodinger equation like solutions, that you get back the correct e to the minus I ej t over h bar solution, right? Which is just kind of the fact that the different energies produce different phases, basically. Okay. So with that, let me actually take the example that we took before again, just one more time. So let me take the Liouville superoperator corresponding to gamma over 2 z rho z dagger minus rho, and you can work out that that simply looks like sigma z tensor sigma z minus identity. And if you write out what that matrix is, it's minus 2 and minus 2 with a gamma over 2. And what that means is that if I take a density matrix rho 1, 1, rho 2, 1, rho 1, 2, rho 2, 2, The dots of them are minus gamma times this matrix, where there's a 1, 1 in the off diagonals, right? So what does this mean? What this means is that if I start in row 1, 1, my density matrix remains invariant. If I start in row 2, 2, my density matrix remains invariant. If I start in any combination of row 1, 1 and row 2, 2, my density matrix remains invariant. If I start in row 2, 1 and row 2, 2, they die within e to the minus gamma. This is exactly the solution we did before as well. So this solution basically is another way for you to arrive at that, the exact solution that we just derived by hand, right? And so the Liouville superoperator theory method seems like it actually has some power to it, has some usefulness to it, right? Yeah, one thing I just want to say is that notice the fact that this thing is blowing up pretty quickly. So if I have a 2 by 2 density matrix, this is a 4 by 4 matrix, because you have to columnize the 2 by 2 density matrix as 4 numbers, and you have to push this into a column. And so this has a 4 by 4 matrix because it's taking a 4-dimensional vector to a 4-dimensional vector. So this blowing up of the Liouville superoperator is actually one of the biggest problems with respect to trying to numerically solve for the Liouville superoperator. So this is something that I just make as a side note. Okay, so how do I solve general Liouville superoperator, general Lindblad equations that don't have exact solutions? What I do is I can first convert them to Liouville space, and then I can give the simple solution for time-independent Lindbladians. I can give the simple solution, which is just an exponentiation. So if I compute the eigenspectrum of L, then this entire solution is present to me, because L is acting as the generator of evolution for density matrices. This is the simple point I just want to make to you. So the only comment I want to make is that L is not equal to L dagger, and this causes some tremendous issues which you have to resolve carefully. There's some mathematical subtlety involving Moore-Penrose pseudo-inverses and so on and so forth, okay? Which I just set aside for the moment. I flagged this as an issue, but I don't talk about it anymore. Okay, so let me go back and tell you what the qualitative variety of solutions that are available are. One qualitative variety of solution that I want to highlight first is basically what are called two-dimensional flows. If you've seen them, then I hope to recap this. If you have not seen them, this is in Strogatz. The figure is 5.2.8, so you can find the appropriate section to look at it, the book on nonlinear dynamics. So essentially all that this says is, it says if I have a two-dimensional flow, so if I have flow in a plane, I have an x and a y direction, and things are flowing, then basically how do I think about the dynamics of this flow? And what Strogatz shows you is that it all has to do with the evolution, the generator of the evolution. So V dot is mv, right? So V is acting as the generator of the evolution. Then just look at the eigenspectrum of M, right? So do a similarity transformation, diagonalize the matrix, and then in the diagonal space, basically what happens is you just have an x dot as dx, where d is now just a diagonal matrix, which means that the immediate solution to this is x of t is just e to the lambda t times x of 0. So if the Lyapunov exponents lambda are positive or negative, then you either have stable solutions or unstable. And if you're on the border, then you have more complicated dynamics. And what this does is it actually partitions the space of the invariants of M, which are the trace and the determinant. It partitions them into separate different sections. So you can have stable nodes, unstable nodes, so on and so forth. Right. So this is something that either you know. If you don't know, then I welcome you to take a look at the section. It's quite transparent. The exact same thing, all I want to say to you, the exact same thing is true in quantum mechanics as well. So what did I just do? I took a 2 by 2 matrix and I vectorized it to a 4 by 1 matrix, and then I took the evolution equation and I wrote it as this, which means e to the LT acting on rho naught is basically the sum of the eigenvalues e to the lambda t times some inner product of the eigenvectors. The only complication here, there may be a notational question that you will have in your mind, is that my left eigenvectors, which I'm calling the equivalent of the bras in Liouville Schmidt space, and the kets in Liouville Schmidt space are not the same. They don't have to be the same. They're a biorthogonal pair. So, and this has to do with the fact that L does not have to be Hermitian. So this is it. That's the only kind of major problem that you will, one of the major problems that you will run into. But just let's ignore that for the moment. And let's assume everything is okay. Then what does e to the lambda t tell you? L is not Hermitian, which means e to the lambda t can be complex. So I have to draw a two-dimensional axis. So this is real lambda and this is imaginary lambda. And all of my eigenvalue structure sits here. And now I can discuss what happens for various qualitative values of lambda. The first of this is what we are looking for, which is lambda, real lambda is equal to 0, imaginary lambda is equal to 0. What does real lambda do? Real lambda simply decays me, e to the lambda, and you can prove for density matrix evolution that lambda can't be greater than 0. So this is the reason why I've blocked out this, this positive lambda axis in red. And so if I have a non-zero real lambda, then what happens is that these are what are called decays, because this corresponds to e to the minus some positive number times t, so it just decays away. On the other hand, if I have non-zero imaginary part as well, then things start spiraling. But whether the spiral, what happens to the spiral? The spiral basically has to decay away because the real lambda is negative, positive, is non-zero and negative. So one family of solutions that decays, pure decays. This is just this is exactly the same as radioactive decay that you've seen. The quantum theory of radioactive decay would just have an e to the minus gamma t exactly like this. These are spirals, which basically mean that as you're decaying, you can also oscillate. You're on your way to decaying. These are the blue dots. The black dot is a steady state, which means that you decay and then you just sit there. And every decaying solution has at least one steady state. That's what we established earlier on. Every spiraling and decaying solution has at least one steady state, excuse me. And then the very last cousin variety of solution, which is exciting and interesting, are what are called oscillating coherences. Oscillating coherences is where the real part of the eigenspectrum is 0, but the imaginary part is non-zero. So essentially, you're going in a circle, and this is like harmonic oscillators, basically. And I can share with you why that analogy is justified later on. Okay, so let me just skip this slide in the interest of time. The only thing I would just want to say is that if I have Hamiltonian motion, right? If I just give you a Hamiltonian, what does a Hamiltonian do? It just has real eigenvalues, which means the evolution is e to the I omega t, which means that if I plot x and p like a harmonic oscillator, quantum mechanical harmonic oscillator solution, I'm just going around in circles, right? And so oscillating coherences are actually this variety of solution. They are also dissipate. They appear in the presence of dissipation, which makes them special. But I just wanted to throw that out there, that the imaginary numbers are essentially the real part of the Hamiltonian, and you should think of them from that perspective. Okay. Okay. So this is basically the school part of it. So I take the last 10 minutes to basically share with you what we are doing with this here at IIT Bombay. And so the question that we wanted to ask was a simple question, which is basically, can you synchronize two oscillating coherences? So synchronization is this phenomenon where basically two metronomes which are oscillating line up with each other and start oscillating in unison. So we wanted to ask, can you do something like that, but for centers? And essentially, not only in centers, we wanted to ask this in a very special case, in a very special scenario, which is essentially what are called boundary time crystals. So with that, I'm sorry, quick introduction to kind of open quantum systems theory and Liouville superoperator theory. Let me come to the last, hopefully 10 minutes of my talk, where I'll share with you briefly what research activity we're doing. And this was recently published in PRL, and the references in front of you, and it relates to something called boundary time crystals. So here on out, I will start heavily hand waving. So please stop me. Please talk to me offline if you want to know more details. I'm more than happy to share them with you. So what I thought would be a kind of a good use of this time that I can share with you is for me to kind of just comment a little bit on what the entire field is, as opposed to essentially my result in the field, which is some small thing. And so I refer to this very nice paper by Kessler and co-authors, and I simply refer you. I just want to walk you through this discussion for a minute. So let me discuss what a thermal phase transition is. A thermal phase transition is where I have a Hamiltonian, and the relevant quantity that I'm interested in seeing is basically the free energy, right? That's the quantity that I want to hold in my hand, because that's the quantity, the differences in free energy are what exhibit themselves, as phases basically, because free energy is the quantity to minimize basically. And the state the equilibrium state that you would discuss in thermodynamics is basically the one that minimizes the free energy, right? And a phase transition is determined as one where there is a non-analyticity of the free energy in the thermodynamic limit. So if you take a large number of atoms, then suddenly there is a non-analytic phase transition, a discontinuity in some measured quantity, right? And this is characterized by this non-analyticity. So this is basically, if you want to draw a picture, if you want to recollect basically Gene Stanley's book or one of these classic phase transition books, then you would say, I had a kind of a phase like that, and then and then I changed some parameters, and then there is a double well that developed, and then that double well is a broken symmetry phase that I go into, right? And a quantum phase transition, on the other hand, is a different variety of creature. Here, what you want to do is you want to look at basically the energy eigenvalues of a quantum system, and you want to look at the ground state energy. And again, the ground state energy shows a discontinuity in some variety of property that it has. And so this basically, there is some characterization of this. I refer you to Subi Sachdev's work if you don't know this. So in exactly the same way, what I want to point out is that there are these things called dissipative phase transitions. And dissipative phase transitions are phase transitions where basically the Liouville zero, so this steady state suddenly changes its shape. So for instance, you go from one variety of Liouville or steady state to another variety. So, these blue lines may be in the thermodynamic limit come and collide basically with the black line, and they make a black dot, and they make a different variety of solution. Sometimes what happens is that this blue dots might simply travel horizontally and hit the red, and so now you have a steady state which has in the thermodynamic limit is oscillating in time, right? You can have these varieties of different solutions. Their entanglement properties can be different, so on and so forth. This is a whole field. That one paper is very well cited. It has over 100 citations, so you can find a lot of literature attached to this area of physics. If you're interested, I'm happy to point several reviews as well offline. Now, what we are interested in just like we were interested in kind of thermodynamic, so the quantities that we're interested in gap closure in the case of quantum phase transitions. Here, what we're interested in is what is called the asymptotic decay rate or the spectral gap. And this asymptotic decay rate is the difference between the 0th eigenvalue, which is sitting there, which has to be sitting there because it's a Lindblad evolution, it has to have a steady state, and the first leading decay term, because this time scale is the inverse of this is the time scale over which the system relaxes to the steady state, right? So that's some sort of metastable or unstable state, transient state, and that basically is the true steady state. So what happens is that in the thermodynamic limit, if that gap is beginning to close, then you really start seeing interesting things. Then what you see is a kind of variety of phase transition that is interesting. How does it exhibit itself in a real paper? Sorry, the reference is in the next slide as well. This is Iamini et al. PRL from a couple of years ago. What you see is basically as you increase the size of the system, as you go towards the thermodynamic limit, the real part of each eigenvalue essentially just collapses to 0, right? So all you're seeing is just travel towards 0, and that's what you should expect. So, with this introduction, what I want to share with you is what the definition of a time crystal is. So a time crystal is basically a variety of symmetry breaking phase of matter, which breaks symmetry in time, basically. So there are two varieties of time crystals. There's discrete time crystals, which I don't want to go into. It's a whole field. And if you Google time crystals, actually what you'll run into are discrete time crystals, I think, more often than not. And then there's this other variety, which are called continuous time crystals or boundary time crystals. And this is, in fact, what I've just been showing you over the last hour. What I've been showing you is the Liouville superoperator theory that you can use to understand continuous time crystals. So what is continuous time crystal? What are continuous time crystals? Continuous time crystals are a property exhibited by open quantum systems. The open quantum systems as a whole, dynamics obeys time translation symmetry. What that means is that the Hamiltonian is time invariant, so it doesn't change in time, and the Lindblad operators don't change in time. So if you look at the Liouville superoperator, at any given point in time, it looks exactly the same as any other given point in time, which means that the e to the LT solution is a solution to the steady state problem that we're trying to find, right? But what happens is that if you take e to the LT, t tending to infinity, n tending to infinity, thermodynamic limit, then the steady state suddenly starts oscillating. And that's the weird object here. And so that's the object of the rest of this, 5 minutes that I have here. Yeah. And so you can take an equation like this. So this is basically what is called the driven decay model. And let me just say that this S minus plus S plus is Sx. So you know actually how to write the solution to this problem already, the analytical solution to this problem. But what you see is that if you take small number of spins, then you basically have something that decays away. But as you go towards the thermodynamic limit, which you see in the dotted line here, oscillations persist, and they persist for infinite amount of time, and that's essentially the boundary time crystal. So this boundary time crystal basically has a phase transition. It's a phase transition, and it's governed by a parameter which is omega over kappa. And for omega over kappa less than 1, it doesn't oscillate like this. It just dies into a steady state. Whereas for omega over kappa greater than 1, it becomes a time crystal phase. So what we did was basically, so this is all what I've just explained here. So what we did was we asked the question, can you couple several of these time crystals and get them to actually synchronize to each other? So can one of them provide the frequency and all the others are basically melted time crystals, and then can you lock them onto each other? And I'll skip over this because it's already too much. But what we were able to show was that indeed this is possible and you can do it. And I point you to this figure as the only thing that is perhaps a takeaway from this part of the talk, which is that we're actually plotting the imaginary part of the eigenvalues and the real part of the eigenvalues of the Liouville superoperator to actually make conclusions about where this time crystal is going. And so from that point of view, all of this is basically you can put it in service tomorrow morning to actually study time crystals, basically. Okay, and there is also some dynamical systems analysis of the criticality of the problem, which I will also skip over. But the thing that I just want to end with is that there is a whole phase diagram that you can actually work out here, and that has a competition between the unsynchronized phase that I have not discussed in this talk. The synchronized phase, which I did just bring up a second ago, and then a melted phase, basically, which is something that I showed you a couple of slides ago. And so what this basically, you can summarize this as a cartoon where basically you start off with uncoupled time crystals, some of which are quiescent, and there's one that's oscillating and that has a given time. And as you go, basically, it shares that frequency with the others. Okay, so let me just summarize that I started basically with some dynamical systems analogy, and these dynamical systems, of course, the physical quantity of interest for us was quantum synchronization. Classical synchronization, of course, is ubiquitous in nature. And what I showed you today was a very concrete method of going from this diagram to the kind of Liouville superoperator eigenspectrum diagram, so that you can arrive at results like this and study synchronization. And where we're trying to take this from a quantum technology standpoint is something like optical memory, so to be able to produce stable optical memories. Okay, so with that, let me just share the conclusions but not talk about them, and I have about 8 minutes to take questions. So are there any questions? Let me just quickly also share the acknowledgements. This is my group, Parvinder, Naufal, Samir, and now Mithun have contributed greatly to this work. And then my collaborators, Mikhail, who's at KO, Sarafazio at ICTP, Manas, Quek, who are at CQT, and Vlatko, who are at Oxford. I've written papers with over the past where I was learning this theory.
Okay, so yeah, so thank you, Dr. Shai, for your intense talk. participants can actually write the questions in the chat box, and also they can ask directly whatever they want. So I don't see anything so far in the chat box. Let us wait for a couple of minutes. So
Okay.
Dr. Chai, just one thing in the meantime, that time crystal can be thought of as a new phase of matter, right?
Yes.
So can you please elaborate for the students? Yeah, if you want.
So as I said, basically, so think of what a crystal is, right? So you have basically in liquid phase, if I have an atom over here and I ask you where is the next atom, well, there is some probability distribution for the next atom to be at a given distance, right? But basically in a crystalline phase, it's periodically arranged exactly one lattice constant away, if you think of a one-dimensional lattice, just for fun. And so crystals in that sense basically break translation invariance, right? Space translation invariance. And so time crystals was originally this was a proposal by Frank Wilczek, that why not basically imagine this kind of breaking of symmetry, but in time. Can you imagine that you have a Hamiltonian which is time constant, but well, actually a Hamiltonian whose ground state basically does something funny. And his original proposal wasn't particularly conducive because of thermodynamics and so on and so forth. But what people have now settled on, so let me just tell you the solution. What people have settled on is two varieties of time crystals. One variety is where you take a physical system, a quantum system, a closed quantum system, and you kick it every period t. But then what you see is it starts oscillating at period 2t, 3t, 4t, some integer multiples of t. And if these oscillations are sustained by many-body correlations, in the thermodynamic limit, if there is persistence of these oscillations, then you have what is called a discrete time crystal. On the other hand, you have a different variety of phase where basically what you have is the Liouville superoperators gap closure produces an imaginary eigenvalue whose real part is zero. And what this means is that expectation values of operators will oscillate in time. And so this produces in the thermodynamic limit, if this happens, if the gap closure happens in the thermodynamic limit, then you have a different variety of phase transition. And so this object is what is what I was referring to as the continuous time crystal. Yeah.
Thank you, thank you. So there is one question in the chat box. Maybe you can read the questions. Are you able to read from the chat box directly?
Yes. So why
Yeah.
is a time crystal formed, Devdutt? And so Devdutt, as I just said, so it's a combination of many body. So it's a combination of many body quantum correlations, essentially stabilizing, and then you have to look at either discrete or continuous to refine this question, right? In continuous, it's the interplay between the dissipators and the Hamiltonian terms that is doing this heavy lifting, basically. Chandramani is asking us, is there any effect of such synchronization on quantum algorithms? So we don't know yet, Chandramani. So let me just say that networks and algorithms related to networks tend to be in a different universe in quantum communication and so on and so forth. And so we have to bring these two communities together. Also, there is one other gap in the conversation, which maybe this is a simpler solution to present to you, which is that if you think of a quantum computer as being as having like some physical architecture, and then there's some software and error correction on top, and then there's algorithms running on top. Typically, quantum communications happens at the algorithms, or network communication happens at the algorithms end, right? So it's about basically having a quantum repeater, and I send some information and gets transmitted downstream, and then I do some protocol basically. And so we are at the physical machine description level, and so again, this gap has to be bridged of traveling up. And so I don't know. The answer is I don't know. Yeah, King Shuk is asking, can the Lindblad type evolution be added in the Heisenberg equation slash picture? Okay, so this is a very good question, King Shuk. So I only described the Schrodinger picture, which basically talks about what happens to the density matrix evolution, the state evolution. So you can ask what happens to the operator evolution. What if I don't care about quantum states, I care about density matrices, then what? I care about operators, then what? Then what happens is that immediately you run into one small piece of problem. So you can write basically trace of A times rho dot and you can take the row dot will have a H row, and you can push it onto the operator, and you can write a dA by dt, right? So you can write an equation for the operator A, and this is typically called the adjoint Liouvillean. The problem with the adjoint Liouvillean, let me just say, because he's in fact even invoked the creation annihilation operator as an example. The adjoint Liouvillean should be such that you now have an A dot, if I think of the annihilation operator A, I have an A dot equation. And so what I need is A dagger is the identity operator, right? So when I take the derivative, this commutator should go to 0. And this is typically not obeyed. And so you need to add back quantum noise to make this consistent, and this is what's called the Langevin picture. And so this quantum Langevin equations, there's a whole machinery, there are books on this and so on and so forth. So I'm happy to kind of point you to some of these resources if you're interested. But yes, there is a consistent but slightly subtle way of kind of moving from Schrodinger to Heisenberg picture. Is there any entanglement in a time crystal? In discrete time crystals, I believe so, even though I'm not really an expert on this. In continuous time crystals, there is a paper by Iamini that I refer you to. So it's the same first author as the original BTC paper. And so, or just contact me, I can show it to you, where they discuss quantum correlations in time crystals. So they have some very nice analysis that I want to share with you. Okay, so there is a question that I'm not an expert on, so I will just skip. I also just want to revert back to Utpal because I'm just about out of time.
Yeah, so we are exactly at 4, and I think you are done with all the questions. So thank you very much, Dr. Sai, for your
Thank you very much.
And
Thank
I'll
you very
also
much
hand
for
over
having
to
me.
the So I'll also hand over to the organizer for the next talk.
Yeah.
Yeah. I hope they're around.
Thank you very much. It's very nice to see you, Otfrid.
Yeah, see you. Bye.
Bye-bye.
Nice to see you, Sai.